We like to define things by what belongs and what doesn't, because change means uncertainty, and uncertainty can be daunting. But stopping change is as impossible as stopping time, and focusing on the impossible is a distraction. What if instead of exclusion, we strove for balance? What if instead of eradication, we focused on utility? What if we embraced our environment the way it is, and we kept embracing it as it continued to change? And what if, when we stepped in to help, we did it not to destroy what doesn't belong, but to put what's out of balance to good use? We need to make invasive species material sourcing as commonplace as organic, post-consumer recycled, grass-fed, free range, biodegradable, free trade, VOC, and hormone-free. It needs to be policy. But first, it needs to be designed. In our region, the Great Lakes region, the introduction and proliferation of zebra and quagga mussels have overwhelmed native species, their habitat, and our infrastructure. Efforts to remove them have been ineffective, and in some instances, even more harmful to the environment. As color and material designers, we wondered, what might happen if we treat them not as a biological threat, but as an overabundant material? We asked, what are they made of, and what can we make from them? Mussel shells are 95% calcium carbonate. Take them up to 1,000 degrees Celsius, and you get calcium oxide. Calcium oxide, lime, sodium oxide, soda, and silicon dioxide, silica, make glass. As bioaccumulators, zebra mussels filter the water. They filter out pollutants and plankton, minerals and trace metals, some of which give glass its color. A glass derived from zebra and quagga mussels will express the color of their ecosystem. Invasion, to region, to chemistry, to color, to identity, to belonging. We collected the first batch of mussels from Lake St. Clair, where zebra and quagga mussels were first introduced in the 1980s. Hitching a ride on ballast tanks of cargo ships from Russia and Ukraine, we boiled them, cleaned them, ground them up, and sifted them into a coarse powder. We worked out the chemistry, the molar calculations for mass and batch recipes. We designed the kiln program to pause on the way up to control the release of CO2 and H2O as sodium bicarbonate transforms into sodium carbonate, which transforms into soda, and as calcium carbonate transforms into lime. And as we paused on the way down and modulated the rate of cooling to swiftly transition through the vitrification range and to slowly drift through the anneal. It turns out the color of Lake Michigan glass is the color of icebergs and tropical atolls, the color of water. We're told it's a copper blue, from the high copper content of Lake Michigan. It's beautiful, and we can't wait to see the color of Lake Superior or Lake Ontario. We can't wait to see each lake, comparing glass from the beach to the lake bottom, taking a biochromatic tour of the water column. We can't wait to rediscover our region through the brilliant blues or greens, or even yellows or rose pinks of what we keep calling an invasive species. And we can't wait to see what we can make out of zebra glass.